Welcome to this talk on the complexity of counting first-order logic for the subword order. My name is Dietrich Kuske. This is joint work together with my student Kuske and Schwarz. Both of us are from the Technische University in Ilmenau, which is a small university in the center of Germany, and that's where I'm sitting on my desk and record this talk. Let's just jump into the content of the paper. So first, let me explain what a subword order is. A word U is called a subword of a word V if and only if U results from V by dropping some letters. So subword, you forget some of the letters of the larger word, of the superword, and some authors call this scattered subword, but I prefer to just call it subword as opposed to a factor. And we denote the subword relation by this less than or equal sign. Here is an example to get an idea of the first levels of the subword order. So the least word is epsilon, then above that you have the words A and B, and then you have all the words of length 2, all the words of length 3, and for instance B squared is above B and this is above epsilon, then there's no further word below B squared, but below BA you have the words A and B and of course epsilon. The subword order is known for its property to be a well quasi-order, and this was shown by Hickman some 70 years ago, and this means that you do not have infinite descending chains, nor do you have infinite anti-chains. But you get the idea up here that anti-chains can get arbitrarily long, but they are bound to be finite. Okay. We are considering in the first part of this talk on the subword order from a language theoretic point of view, and therefore I'm now recording some results from language theory. First of all, a folklore result. If you take a regular language and you take the set of all subwords of elements of L, the downward closure, set of all words that have some superword in L, then this downward closure is effectively regular again. You can construct an NFA for the downward closure from an NFA for L. Similarly, the upward closure, which is the set of all words W that happen to have some subword in L, is also effectively regular. So you take the language L, you take everything below it or everything above something from L, and both these languages are effectively regular. Karen Descartes and Schneebelin introduced and investigated the incomparability set. That's the set of all words W such that for at least one element of L, W is neither a subword nor a superword. And we denote this as V and W are incomparable. So the incomparability set is the set of all words from A star that are besides, say, some word from L. And they showed that also this set is effectively regular. Last year, Georg Zetsche and myself generalized these three results. We didn't consider just the downward closure, but a threshold downward closure, where the difference is that we collect all words W that have at least T many superwords in L. So not just one, but at least T many. And similarly for the upward closure and the incomparability set. Above, below, incomparable with, at least threshold many words from the language. And we showed that also then the resulting language is effectively regular. And of course, for T equals 1, you get the results up here. This is again Zetsche and myself from last year. And this is what I wanted to tell you about regular languages. Now, let's go to or look at piecewise testable languages. And here you have similar results. Karen Descartes and Schneebelin in 2016 showed that if L is piecewise testable, then the downward closure, upward closure, and the incomparability sets all are effectively piecewise testable, and the height is polynomial in the height of the language L. And I'm going to explain what piecewise testable and polynomial height means on the next slide. Now, the main result, the first main result from this paper I'm talking about is that if L is piecewise testable and T is some threshold, then also the threshold, downward closure, upward closure, and incomparability sets are all effectively piecewise testable of polynomial height. So, in other words, for T equals 1, we generalize the result by Kerendikant and Schneeberlin to arbitrary T. Now, what does piecewise testable mean? What does polynomial height mean? To explain this, we need Imre-Simons congruences and, of course, then piecewise testability. So, first, the congruence. Let n be any index, any natural number, and u these two words. Then the words u and v are n equivalents at level n, if u and v have the same subwords of length at most n. So for any word x of length at most n, we have x as a subword of v if and only if it's a subword of the other word. So u and v have the same subwords of length at most n. And here's some example with a word in square brackets with an index. I mean the equivalence class with respect to this equivalence relation of index 2. Then AB is the only word that's equivalent with AB, since it's the only word such that the subwords of length 2 are just A and B and AB. Now, if you consider the equivalence class of index 2 of the word AB squared, then you get the set of all words that start with an A, continue with 2 B's, and then have an arbitrary number of B's. And here's a last example. If you now append an A, so you consider the word A, B square A, then all the words where you can plug in behind the second B an arbitrary number of B's are equivalent to A, B square A, since as subwords of length 2, they have all the words of length up to 2, but also all the words of the form B, A squared, and then arbitrary many A's and another B form words that are equivalent with A, B square A, since they contain all words of length at most 2 as subwords. 3 examples of equivalence classes. Now, Simons congruence is precisely this equivalence relation. It's a congruence with respect to concatenation of words. And it is easily seen that it has finitely many equivalence classes, a property that we are going to need in the next definition. It's an equivalence relation, even a congruence, and has finitely many equivalence classes for every n. Now, a language L is piecewise testable of height at most n, if and only if it's closed under Simons congruence of index n. In other words, if and only if it is a union of equivalence classes of this congruence, and since there are only finitely many, this language is piecewise testable of height n, if and only if there exists a number k and words w1 to wk such that L is the finite union of the equivalence classes of the words wi. Piecewise testable of height n. And now, the first main theorem that in particular language theorists should look at. Let L be a language that's piecewise testable of height at most n, and let T be a natural number, a threshold. Then the threshold upward closure, the threshold downward closure, and the threshold incomparability set, all with respect to T, are piecewise testable of height polynomial in n. So here we have a closure property of the class of piecewise testable languages. Here's the proof idea. So L is piecewise testable of height at most n. Therefore, L is a union of equivalence classes of the equivalence relation of n, level n. And since equivalence classes are mutually disjoint, we have a disjoint union. Now let this double arrow be one of the three operations or comparability relations we are interested in. Then the threshold version of the upward closure, downward closure, and comparability set of L is a Boolean combination of the corresponding operation applied to the equivalence classes. Well, with smaller, possibly smaller threshold. The idea is that if t is 2, and this is the downward closure, then a word has at least 2 superwords in L if it has 2 superwords in the first equivalence class, or 2 in the second, or 1 in the first and 1 in the second. So therefore, it's a Boolean combination. In other words, we only need to prove this theorem in case L is a single equivalence class. And here we make a case distinction according to the form of the equivalence class. And what one proves first is that there are actually 3 main classes of equivalence classes, 3 main types. Namely, the equivalence class is a singleton, and we saw such an example on the last slide. Second example, or the second type, the equivalence class is a single convex chain. So it's a chain, linearly ordered, and it's convex if you have 2 elements in this chain and some words in between the 2. Then this word already belongs to the chain. It's a chain and it's convex in the order theoretic sense. And the last type says that the equivalence class, now it's more complicated, but it contains 2 convex chains. These 2 convex chains might intersect, but only in a minimal element, if at all, in a minimal element of the equivalence class. And the third property is that they are in a sense maximal chains in the equivalence class, that is, they are infinite and go down to some minimal element, so it cannot be extended downwards. And as before, both of them are convex. One first proves this classification of equivalence classes, and this makes heavy use of insights by Imre Simon from his PhD thesis and by Carenticant and Schnebelin from their paper on piecewise testable languages. And then extends their result, in particular the third case. Having this classification, one proves the first main theorem, so these closure properties for each of these 3 cases, and then one is done, and I won't explain how to handle the cases one by one. Now, this is the main result for language theorists, and now I'll use it in logic. So in logic, I consider predicate logic, so I need a structure, and the structure is this one. We have the universe, the set of all words over the alphabet A. We have the subword order. We have a regular predicate for every NFA, and we have a constant for every word. This is the structure I'm going to study. Now, we can express properties using some version of first order logic. What can we do? Well, we have variables or words x1, x2, and x is a variable a and NFA. Then we can say that x1 is a subword of x2, either a variable or a word. x1 is accepted by the automaton A. We have Boolean combinations as usual, and we have quantification, existential and universal quantification. These are the formulas, and now this is first order logic, and one could ask whether the first order theory of this structure is undecidable, and indeed it is, even if you only have the subword order and not the predicates and not the constants. So we have to restrict attention to fragments of this logic, and here is one fragment, FO2, and that's first order logic, but only two variable names. You can only use the variable x and the variable y. You can reuse them by quantification, but you only have these two names. That's FO2. And then C2, counting extension of first order logic with two variables. Again, you have only the variables x and y, but now you only also have a quantifier that says there are at least t many witnesses for the rest of the formula. For instance, in FO2, you cannot say the set has at least 3 elements, since for that you would need 3 variables. They are x, y, and z, and they are pairwise distinct. In C2, you can express this by simply saying there are at least t, or at least 3 many x's, such that x equals x. C2 is more expressive than FO2, at least in general. Now, some known results in this context. First, Quantifiers and Schwarz in 2015 showed that the FO3 theory, 3 variable names, x, y, and z, and no thresholds, is undecidable even without regular predicates or constants. A remarkable result. What makes this result even more remarkable is the positive counterpart, namely that the FO2 theory, only 2 variable names, becomes decidable, and then you can even add regular predicates as well as constants. Very same paper, FO2 theory decidable, FO3 theory undecidable, even without constants and predicates. Now, this decidability algorithm is seemingly non-elementary, and Kuske and Schwarz in 2016, so the year after, identified a case where it's elementary, namely the FO theory becomes elementary if you drop the regular predicates. So if you only have the constants and the subword order, then the theory becomes decidable in threefold exponential space. This is the situation for FO2. I already mentioned the paper by Georg Zetsche and myself from last year, and what we did there was we extended this result up here, the decidability, from the FO2 theory to the C2 theory. The C2 theory of the structure together with predicates and constants is decidable, and as in this case, our algorithm is non-elementary. And the second main theorem from this paper, and this time of interest to logicians and possibly algorithm people, is that the C2 theory of the structure without regular predicates has quantifier elimination, typical result or notion for logicians, and is in twofold exponential space. Forgetting about quantifier elimination, the C2 theory of the structure without regular predicates is in 2x space. This improves the result number 3 by Quantifiers and Schwarz in 2 aspects. First, we save one exponent. Our algorithm is exponentially more faster, uses less memory, and we add threshold counting quantifiers. So first, quantifier elimination, since we need this for the algorithm. A lemma, let phi be a C2 formula with just one free variable y, then the set of all words that satisfy phi, L sub phi. The set of the language that's defined by the formula phi. This language is piecewise testable, and the height is doubly exponential in the size of the formula phi. Any language defined in C2 is piecewise testable. And here's the proof idea. one proceeds by induction on the construction of the formula phi, and the interesting case is if the formula starts with a threshold quantifier. Then by the induction hypothesis, we can assume that phi dash is a Boolean combination, or even in disjunctive normal form, over the atomic formulas x is a subword of y, or vice versa. X belongs to K, Y belongs to L, where K and L are piecewise testable. And now we distinguish the cases X is a subword of Y, Y is a subword of X and Y are incomparable, or X and Y are the same in phi dash. And doing some basic messaging of the resulting formula, we get that phi of y is equivalent to a Boolean combination of formulas of the form y belongs to L, and there are at least as many words in K that are all superwords of y, subwords of y, superwords of y incomparable with y, or kind of strange, equal to y. Now, this formula here says y belongs to L and y has at least as many superword, subword, incomparable words in K. So in other words, this formula is equivalent to the formula y belongs to L intersected with K closure, S-fold closure applied to K. In other words, L phi, the set of words satisfying phi, is a Boolean combination of such languages. And since by the previous theorem, this language here is piecewise testable of bounded height, and piecewise testable languages of given height are closed under intersection, actually under Boolean combinations, the lemma holds. Any language that's definable is piecewise testable of height doubly exponential in the size of the formula. Now, since piecewise testable languages can be defined in our structure without using quantifiers, since we have the words here, what we get is any formula phi is effectively equivalent to some quantifier-free formula that uses constants of length doubly exponential in the size of phi. This is the quantifier elimination result. Any formula is equivalent to a quantifier-free one. Even effectively, we can build this quantifier-free formula, and in this construction we introduce new constants, but we can bound their length, namely it's doubly exponential in the size of phi. This gives the quantifier elimination result, and the final result, the decision procedure. So the second main theorem, part 2, says that the C2 theory of the structure without regular predicates but with constants is in twofold exponential space. And here's the proof idea. We do a naive evaluation of the formula phi. So when we have a conjunction, we evaluate the two subformulas and dive into the formula. And the crucial case is what happens if the formula phi starts with a threshold counting quantifier, or actually any quantifier. Then we would have to check or count the number of words x that satisfy phi dash. For this we would have to investigate, consider every word, but there are infinitely many. So here we have to do something, and if we look into the proof of the previous lemma, then we see that phi is equivalent to a Boolean combination of formulas y belongs to L, and there are at least as many superwords, subwords, etc. of y in K. And now we look at a result by Keren-Dican and Schneeberlin, extended slightly, but essentially it's their result. And then we see that we do not need to look at each and every possible word x in K, but only to those of bounded length. And then the result is, in order to evaluate phi, in this case, it suffices to verify words x of bounded length. And if you formulate this out completely, or do all the calculations, then you will see that the words are bounded in doubly exponential. And now we come to the summary. The two main theorems for language theorists giving closure property of the class of piecewise testable languages, and for logicians giving quantifier elimination and elementary decision procedure. And the first question everybody would ask, and here's the answer: is twofold exponential space optimal? And my honest answer is I have no idea. The best known lower bound, again by Karin Descartes and Schneeberlang, is P space. Thank you very much for listening and watching, and I'm looking forward to the discussion that we will have over the internet. Thank you very much.